Hello everyone, it's fantastic to be here. Welcome to my home, which is on the traditional land of the people of the Eora nation, and I would like to acknowledge their elders, past, present and emerging. Today, I want to talk to you about the work that the Transformational Bioinformatics Group at CSIRO have been doing. In that work, science and technology collide. Now, science has been transforming for a while. It has become more digital, it requires global collaborations, and it demands that the general public has an input. So the question is, are we ready for all of this? I think we actually are. So at CSIRO, we are Australia's government research agency. And we're very passionate about translating research into products that people can use in their everyday lives. For example, one of CSIRO's most famous products is Wi-Fi, which CSIRO invented together with Macquarie University and is now used in over 5 billion devices worldwide. CSIRO also invented the first influenza treatment, Relenza, together with Monash University. And on a lighter note, CSIRO developed the Total Wellbeing Diet, which is now on the book bestseller list alongside Harry Potter and the Da Vinci Code. So I think from that perspective, we do have a nice balance between products that people enjoy and products that people need. Today I want to tell you about three stories that highlight what kind of technologies are transforming science. Those are artificial intelligence, which we are using in genomic medicine, genome engineering, which we are using for genomic surgery, and cloud computing, which is for more resilient economies, and we're using it for global collaborations. So the quote that really resonated with me around artificial intelligence is that AI is the new electricity, meaning it's so ubiquitous that every industry actually will use machine learning going forward. So therefore, it's no surprise that we're using it for genome analysis. Specifically, we're part of the Project MIND consortium, which is the largest genomic consortium for a single disease in the world. And that disease is a motor neuron disease, ALS, that Stephen Hawking suffered from. Here, the aim is to identify the genetic cause of this heinous disease. We're using machine learning in order to identify what kind of genetic differences are between the people that develop ALS and the healthy general population. The reason this is difficult is because the genome is a vast space, and we are requiring a large amount of people or information from a large amount of people in order to really find this needle in the haystack, find the disease gene that is driving ALS. Frost and Sullivan have estimated that by 2025, 50% of the world's population will have been sequenced, which means genomics will be producing more data than the traditional big data disciplines, YouTube, astronomy and Twitter combined. On one hand, this is exciting because for the first time we will be having the amount of data necessary to understand a complex disease like ALS. But on the other hand, it's quite scary because as health researchers, we're not used to be at the forefront of big data compute. But as researchers, that is what we do. We take on a challenge, we adapt to it, and we develop a solution. And this is exactly what we've done with Varian Spark. So Varian Spark is a machine learning library for big data. We showed that it is 3.6 times faster than the traditional approaches that are out there developed by Google and Yahoo. And I'm showing here in this graph, I'm plotting the runtime against dataset increases. And what you can see is Varian Spark is the dashed blue line and the yellow line is growing sublinearly with the dataset sizes, whereas other technologies grow exponentially, meaning they cannot scale to the dataset sizes of the future. And we showed that in that dataset sizes of the future, would take traditional approaches 100,000 years to process, whereas Varian Spark, with its new algorithm, can process that kind of data in 15 hours. So bringing this awesome compute power to the Project Mind consortium, we were able to confirm certain disease genes that are already known, but we also were able to identify new ones. Here we were able to consolidate or bring together family units that were thought to be unrelated and bring them together, and with that additional power we were able to identify 2 additional disease genes for ALS. And this is important because in ALS, from diagnosis to death usually is only 2 years. So people need to be diagnosed quickly and put on the right treatment as soon as possible. And hopefully these new disease genes actually helping and accelerating that process. We also applied Varian Spark to COVID-19 in order to answer the question whether COVID is mutating in a way to make it more virulent or cause more severe disease. Specifically, we identified 300 individuals that had a severe case of COVID and 200 individuals that had a mild case. And the question was, is there something in the virus genome that might be predictive of the outcome? Using Varian Spark and analyzing the data, we did find the well-known D614G mutation, which is in the spike protein and has already been associated with potentially being more virulent. However, analyzing this kind of data really requires more information. 500 individuals are not going to give us the information needed in order to pinpoint mutations that are functional in the 30,000 bases of the virus genome. So we will need to wait and see until we have more data available before we can reanalyze that kind of data and get more insights into how this virus behaves. This brings us to the second story around genome engineering. So the quote that I chose here is from Jennifer Doudna, who very topically won the Nobel Prize in Chemistry along with Emmanuel Charpentier. And she said, "The world around us is being revolutionized by Crispr, which is this genome engineering technology." But she also says that it is revolutionized whether we're ready or not. And I think this is a quite telling quote because technologically there will be a lot possible. But the question is, do we really want it? As a society, is that what we aim for? Now, we applied this technology in genetic surgery approaches, specifically for gene therapy. There, the idea is that the CRISPR technology is going to a specific tissue and correcting the misspelling that is causing a genetic disease only in that particular tissue. And this is work that we're doing together with Westmead and the Children's Medical Research Center there. They are specifically interested in a liver disease that is causing children that are diagnosed with that to unfortunately die. Therefore, being able to develop a treatment, a life-saving treatment, would really be a game changer. Now, what is involved in order to develop such a new or trailblazing such a new treatment course? Well, first of all, we need to identify what kind of mutation is actually causing the disease and which tissues are affected. Then we need to identify how to best target this particular misspelling, so how to guide the genetic machinery to this particular location, but also how to wrap up this machinery into an envelope that only delivers it to this specific tissue rather than body-wide. After those two things have been resolved, we do need to generalize this approach so that other people that might have changes in their genome would also benefit from the same treatment approach. Then it would go into preclinical work as well as the clinical trial phases 1, 2, and 3 before it actually can be administered as a new treatment course. Now, CSIRO is involved in the middle bit in identifying how to best target the mutation and how to make this as efficient as possible. Now, CRISPR is also used in the diagnosis of COVID-19, specifically in identifying a specific marker of this particular coronavirus strain and differentiating it to other coronaviruses or other viruses out there. We developed a computational technology in order to make this more specific and make it more reliable. Meaning that we identified locations in the coronavirus sequence that is very amenable to attracting the CRISPR technology, therefore reducing the false negatives, but also highly specific to this particular coronavirus compared to other viruses out there or other strains of coronaviruses, therefore reducing the false positives. Those two things need to be balanced for a clinically relevant test that can be then applied, hopefully in the future, lab-free, like a pregnancy test. This brings us to the third story around cloud computing. Now, Gardner said that in a post-COVID world, designing for resilience is more important than designing for efficiency. And we agree with that. Our strategy in order to deliver resilient research is to go to the cloud. Now, I couldn't find a cloud quote that quite encapsulates how I think or how we treat the cloud, because cloud to us is not a technological solution, but it is a mindset. Cloud is creating a more collaborative way of generating knowledge and doing business. Meaning, yes, it is more cost effective and we can scale to massive workloads. Also true that we can access new technology easier without having to have an upfront investment in it. For example, we can be using GPU clusters without having to install one in-house. But to us, the most important element of cloud computing is that it connects us with the world, and we can do research in a collaborative way like never before. Coming back to the cost effectiveness though, here in this particular use case we demonstrated that researchers or a research institution would have to spend $4,000 a month in order to provide a specific genomic service. Now, using serverless or cloud native approaches, we can bring that down to just $15, meaning for less than a cup of coffee per day, research institutions can deliver knowledge to the world using cloud and serverless technology in particular. This is a real game changer for academic research, because now for the first time we can box up everything in infrastructure as a code, meaning the compute environment, how a software is installed, how the user permissions are set, how the data is kept safe. All of this is not a discovery that an individual researcher needs to be made by themselves, but it is knowledge that can be shared between researchers. So what I'm visualizing here is that this infrastructure as code template can be shared with other researchers and then automatically stand up the right environment, the right analysis code, and the right triggers for analyzing data can be deployed automatically in the hands of other people. So when papers are published in the future, I would imagine that the environment and the whole building plan of how to do this analysis are also shipped alongside with it. We specifically have done that for Varian Spark, the machine learning library we've been using to analyze ALS data. It is available on the AWS Marketplace, where users can subscribe to this particular service, and it automatically gets deployed in their user account, meaning no one else has access to their data or the analysis or the results. Everything that is done with the data and the result of the data remains within their cloud account. This is of course important for sensitive data like genomic data or other medical data, but it's also a convenience thing because again, the researchers don't have to reinvent the wheel. They can use the industry best practice in order to keep their data safe. Now, the 3 things I hope you take away from this talk is that science has been accelerated through technology, but we need to constantly reinvent ourselves. We need to constantly learn new skills in order to really make the best use of the technology around us. But greater capability also means greater responsibility to do the right thing. Just because cloud computing, artificial intelligence, and genome engineering can enable a certain application case, we do need to spend time in order to evaluate whether this is what we want and what the consequences will be. And this includes consulting with the general public. Now, technology has become more collaborative. Research has become more collaborative. So the question is, how can you and us collaborate better? Contemplating that question, let me wrap up this talk by thanking the fantastic team that I am working with. And let me refer you to my Twitter account where I'm sharing our research findings and other news. For example, the program has recently released 2 reports, one around how we're using AI in the health sector, listing 32 case studies of how machine learning and AI is applied effectively in order to improve healthcare and health services. And the other one is our annual report showcasing what the 100+ researchers and engineers working for the program, how they're contributing to Australia's healthcare system and improving the technologies going forward. With that, I'm looking forward to the Q&A session, and I'll see you there.